Okay, hi guys, welcome to my video on how to split test your life, and I'm just going to go over how we determine confidence intervals so that you can tell if you have statistically significant results. And this goes along with the article I was writing on this topic, so if you're on YouTube, please check that out. It's in the description. It'll make things make a lot more sense. Otherwise, let's get going. So the first thing that I've done is put my data into Excel. Okay, this is the sample number. Okay, so I have 20 samples, and this is for route A and route B. Like I said in the article, we're using an example of driving to work. We want to see which one's faster. Okay, so what I've done here is hypothetically recorded uh, 20 times going route A and 20 times going route B, mixing that up appropriately to ensure enough randomness. Um, so basically the point of this is we want to see which one's actually faster. You'll see sometimes route A is faster, but sometimes, route B is faster in this case, but it's much slower in this case. And you're going to see on days there's going to be variance. So if you actually want to know which one's faster, we need a statistically significant result. So that's what this is checking for. Okay, so I have this formula up here. It's in the article. I just put it here for reference. And the point of it is we want to basically fill this out, and this is going to give us a confidence interval of the time it takes to go to work. And we're comparing the two routes together and seeing if we actually have a faster route or if we don't have enough data to make it conclusive. Okay, so I'll start off defining these really quickly. X1 is the mean or the average of our first method or our first option, which is route A. So we're going to have to get the average here. If you have it in Excel, this is obviously really easy. So you stick that in. So that's our X1. X2 is the exact same thing, but for our second option, which is route B. So go ahead and do that too if you have data. Then next we have this t. Now this t isn't a variable related to our data, but what it is a statistics variable. Okay, I've linked to this a t-chart on the article, and I mean you can Google them; they're all the same. Doesn't matter. And what this tells you is the probability of the mean actually being in this t region. Okay, so your mean, your average would be somewhere right here in the middle, and then as you go farther away from that, the probability of it actually being, this amount when your testing has shown this, it's very small. So this helps us apply some statistics to our data. I mean, you can go into more detail if you want in any statistics textbook. But for now, we're just going to take a value from it. It's very simple. It depends on these two factors. Okay, we have alpha divided by 2 here. Okay, so alpha is our basically confidence that we want, and typically we're going to take a 95% confidence. Okay, so this means 19 out of 20 times we're going to have the right result. And you can do higher, but the problem is you aren't going to get significant results like we'll talk about later unless you have a lot of data, which could be an issue. But in this case, we'll use 95%, so our alpha becomes 1 minus that, okay? 1 minus 0.95. So alpha is 0.05, and for this table, we want to divide that by 2, because there's 2 ends of the distribution, the right and left side. Okay, degrees of freedom is also very easy to get. All you want to do is look at the number of samples you have, whichever is less for the two routes. So in this case, I have 20 for both of them. Let's say I had only 15 for A, I would be looking for that one. So the lower number, in this case, is 20 for both. So I'll use that. And to get degrees of freedom, you just use that number and subtract 1 from it, okay? So 20 minus 1. And then we go back to the chart. So we have 19 degrees of freedom and 0.025 for our tail probability. So degrees of freedom, we go all the way down here to 19. Then we go over, and we want to keep going until we get this tail probability of 0.025. Okay? And then we take that value, which is 2.093, and we write that down. Okay? So then this last portion is your standard deviation of your first option squared divided by the number of samples you have for that first option. So for root A, we need our standard deviation. If you have Excel, just plug in the formula. You can use online calculators too if you don't. And we're going to do the exact same thing for root B. Okay, we get those values. So now we have everything in this formula, and all we need to do is plug it in and we can get our confidence interval. So the first thing I'm going to do is calculate this x1 minus x2. So this is really xa minus xb, our two roots. So you get that just from your averages, 15.3 minus 14.15, nice and easy. And then we're going to calculate this whole thing on the right, okay? And to do that, we multiply t by the square root of the standard deviation of root A squared over the number of samples, which is 20. So we take this and divide by 20, and then we do the exact same thing for root B. So square the standard deviation, 1.22, and divide by 20 because we have 20 samples again. So once we have that, we want to look at this plus this and this number minus this thing on the right, okay? And the lower limit will be this minus the stuff on the right, and the upper limit will be the difference plus the stuff on the right. Okay, so this is what this tells us, is that the difference between the two means in actuality, okay, this is our sample means, but like in real life, the statistically defined mean is going to fall within this range when we subtract them. And this actually gives us a statistically significant result. And okay, here's the most important thing if you get anything, is if we subtract x2 from x1, we are looking at how much bigger x1 is than x2. If the lower limit, okay, think of it on a number line. 0 is in the middle, you have negative numbers here, and then you have something like 0.5, 1, 2. So in this case, our lower limit is right around 0.5, it's right here, and our upper limit is right around 2. So at no point do we cross the 0 line, and that's what's important here. Our difference is somewhere in here, but it definitely doesn't have a 0. So what that tells us is x1 is always bigger than x2, and we're 95% sure of that, and that goes back to our t-value. So in this case, we would make the conclusion that x2, or the mean of x2, or root b, is bigger than root 1. And what this means is that we would obviously take root b because it's faster. So, and just to kind of, this is a fairly realistic example, okay? It's 1.15 minutes faster. But you have to add that up, 2 times a day, 20 times a month, and you're gonna save over 4 or 5 hours just from that. And if you apply this for a bunch of different things, then you can save a lot of time by doing this easy testing, and it's a really good investment of your time. So just the one final thing I want to do before I end this video is make it clear, if you had results where your lower limit's negative 0.5 and then your upper limit is 1.8, I just want to be really clear about this. This would not be significant. Okay. Okay. Sorry, it would be significant, but it wouldn't give us a result of which one's faster. Based on this x is somewhere to the left of 0. The actual difference between the two roots, either one could be bigger than the other. That's what that tells us when we have 0 in that range. Okay, so just always come back to that point, and you can figure out what your data is telling you. And it's really important that you interpret it correctly. Okay, I hope that was clear, but if it wasn't, leave me a comment, YouTube or on Savings Village, and I'll definitely get back to you and hopefully clear it up. Okay, thanks for watching.